Okay, now for the structured questions. Okay, so for section A, I believe it's quite straightforward. Okay, for part A, A part 1 is just a metal plus acid reaction. Okay, which gives you salt and water. Okay, salt and hydrogen gas. Your salt is just your hydrochloric acid hydrogen replaced by the metal potassium. So you get potassium chloride hydrogen gas. Okay, next is magnesium carbonate plus sulfuric acid. It's an acid plus carbonate reaction to give you salt, water, and carbon dioxide. Salt form is magnesium sulfate. Okay, carbon dioxide, water. Okay, calcium oxide plus hydrochloric acid is a base plus acid reaction which gives you salt and water. The salt is calcium chloride. Okay, and the plus water. Okay, next one is sodium hydroxide plus ammonium nitrate. It's a ammonium salt plus alkali reaction to give you salt plus ammonia plus water. The salt form is sodium nitrate. Then you get ammonia gas and water as well. Okay, for B part 1, okay, to balance it, remember it is a base plus acid, you get salt and water. Okay, the salt form is lithium chloride because lithium is in group 1, it's a Li plus. Okay, then you get LiCl plus H2O, just balanced by placing 2 in front of HCl and LiCl. Okay, next, zinc plus sulfuric acid is a metal plus acid reaction to give you salt plus hydrogen gas. The salt form is zinc sulfate and you get hydrogen. No need to balance, it's already balanced. Okay, part 3. Okay, you have copper 2 carbonate. How do I know it's copper 2 and not copper 1? Because it has to balance out the charge. I have CO3 2 minus and Cu2 plus. Okay, plus HCl is an acid plus carbonate reaction to give me salt, carbon dioxide, and water. The salt form is copper 2 chloride, so CuCl2. Okay, and I get CO2 and H2O. To balance it, I place a 2 in front of HCl. Okay, last one, part 4. Okay, you have calcium hydroxide, okay, plus ammonium chloride reaction. Calcium hydroxide is an alkali. Okay, ammonium chloride is ammonium salt, so you'll get salt plus ammonia gas plus water. The salt form is calcium chloride, CaCl2, and you will have, and then you need to balance by placing 2 in front of ammonia and ammonium chloride. Okay, how do we balance this easily? You just balance by the nitrogen atom first. Okay, so no matter how many moles of ammonia is formed, you will form the same number of moles of you will require the same number of moles of the ammonium salt. Okay, question 2. Methylamine gas reacts similarly to ammonia gas when dissolved in water as shown below. Okay, you see it's very similar to your ammonia. And then you have calcium hydroxide dissolved in water, okay, to form Ca2 plus OH, 2OH minus. What is the first thing that I notice? I see the reversible versus single arrow sign, which means that methylamine is a weak alkali. Okay, remember, because both of them are giving off OH minus ions, they are alkalis in water. And this is a strong alkali. Okay, so part 2A asks what would you observe if the following are added. You must talk about the initial color. Okay, when you say observation, it's always initial color and final color. So in this case for litmus, you must tell me that red litmus turns blue because it's an alkali. Okay, universal indicator, original color is a green solution. So green color will turn blue because it's an alkali. Okay, part B, with reference to the equation, state and explain whether calcium hydroxide solution or methylamine solution has higher pH value. Okay, when we're talking about higher pH, since they are both alkalis, we only look at the strength. There's no need to compare concentration or amount of moles or whatever. Okay, just look at strength. Okay, so you just have to tell me calcium hydroxide has higher pH. Okay, why? It's a strong alkali. Ionize completely in water to produce more hydroxide ions compared to methylamine, a weak alkali, which only partially ionizes in water to give off hydroxide ions. Okay, next question 3. They say red grapes contains a number of colored pigment which can be separated using a solvent. A weak dibasic acid known as tartaric acid can be extracted from grape juice. Structure for the tartate ion is represented below. Okay, with the use of an equation, explain why tartaric acid is a weak dibasic acid. Okay, first you have to start with the acid, and since it's a weak acid, it have to be reversible sign. Okay, you know that it will give off hydrogen ions. So remember, each hydrogen ion is a H+. in order to balance out this tartrate ion, which has 2 minus on both sides, on each side with a COO, you need to pair a hydrogen on each side. Okay, so this as a whole is your tartaric acid. Okay, when it dissociates in water, it will ionizes in water, it will form 2H plus and the tartrate ion. So 2H plus and the tartrate ion. Okay, why is it a weak dibasic acid? First, you need to tell me that it's partially ionizes in water, and they want to use the equation. So how do we use the moles here and explain? You cannot tell me 1 mole of tartaric acid will give me 2 moles of hydrogen ions, because that is under the assumption that every mole of tartaric acid will ionize. So you have to split it into 2 portions. First, tell me it ionizes partially. Second one, for every mole of tartaric acid that ionizes, okay, for every mole, you will produce 2 moles of H plus ions. Okay, so remember, for weak acids and weak alkalis, they do not completely ionize. But for those that ionize, they will still fulfill the mole ratio in the chemical equation. Okay, for part 2, describe a chemical test to show that tartaric acid is weaker than a strong acid. So chemical test cannot be adding indicator. That is not a chemical test. So some of you managed to get it. You have to add something to react with the acid, and you observe the intensity of the reaction. So you can either add magnesium metal, or you use magnesium carbonate, or any suitable reactive metal. Okay, if you use magnesium oxide, there's no way to see the intensity, because it will form water and salt, and you cannot observe effervescence from acid plus base reactions. Okay, so when you react with tartaric acid, you will notice slower or less effervescence or gas bubbles form, because okay, the weak acid will give off less H plus, okay, to react with the acid. Therefore, the rate of hydrogen bubble production is slower, so you will see lesser effervescence, okay, which is the rate of the formation of the bubbles. Okay, take note that eventually you will still react completely, because the reaction of a weak acid with a weak acid with a metal is still complete. For example, if I use a weak acid like, okay, I use ethanoic acid plus magnesium, I will still form, okay, sorry, I'll form magnesium ethanoate. And this reaction, notice, it is one way, it's irreversible. So for every H plus from your ethanoic acid that has successfully ionized, okay, it will react with your magnesium and forming your salt and hydrogen gas. And eventually, all of the acid, weak acid, will also be reacted away. Okay, so when we compare weak versus strong acid, we are only looking at the intensity of the reaction, because of how fast or slow the H plus is being given out. Okay. Part B. Figure shows how electrical conductivity changes when potassium hydroxide is added to aqueous tartaric acid. So I think for most of you, you actually didn't really understand what the graph means. Okay. If you look at the y-axis is volume of K potassium hydroxide added in cm cube. And for the y-axis is conductivity in milliamperes. Okay. So along the y-axis, whereby when you have 0, okay, when you don't even have potassium hydroxide added yet, as it is only your tartaric acid. As you slowly add potassium hydroxide, what is happening is, when you add potassium hydroxide, you are reacting with tartaric acid to form, okay, your potassium tartrate, your salt. And notice this salt is aqueous. You also form water. Okay? So, with reference to your answer in A part AI, explain the low conductivity. A lot of you didn't refer back to the previous answer, whereby you have to talk about the partial ionization. You just wrote in your own words. Okay, so you have to tell me that tartaric acid is a weak acid, ionizes partially in water to give fewer mobile ions to conduct electricity. Therefore, the conductivity, while present, it is low. Some of you said that there's no conductivity at all. Not true. As long as I have H plus, mobile ions or mobile electrons present, I can conduct. Okay, it's just that the more I have, the better my conductivity. Okay. For part 2, explain why the electrical conductivity increases from S to T as you add potassium hydroxide to the aqueous tartaric acid. Okay, a lot of you said that because you add sodium hydroxide, you are adding OH minus ions which are free to move. While that may be true, whatever potassium hydroxide you add is immediately reacted with tartaric acid to form potassium tartrate. So what you're saying is false. Okay, there will not be any potassium hydroxide hydroxide ions available to conduct electricity from S to T because they have all been used. Okay, they have all been used to form your potassium tartrate. Okay, so what actually accounts for this conductivity then? Okay, you look at the salt form. The salt form is aqueous, which means that this aqueous salt can also ionize to form 2K plus and your tartrate ion again. And these two ions are mobile and they can conduct electricity. So as you add potassium hydroxide, you are not increasing the conductivity by increasing the amount of OH minus ions in the solution, but rather providing even more ions maybe more ions to conduct electricity. Okay, of course your acid is also used up at this point. Okay, so the answer for part 2 will be the salt form is soluble in water, presence of increased more mobile ions because the salt can ionize as well. It's aqueous. Okay, part 3, explain why the gradient of line ST is less steep compared to TU. A lot of you didn't compare the steepness, but you only explain why TU will have there is electrical conductivity at TU. Okay, so you managed to say that at point TU, okay, from at TU, the potassium hydroxide is already added in excess. Therefore, there's mobile hydroxide ions to conduct electricity, but you didn't compare it to when it was at ST. Why is TU steeper than ST? Okay, remember ST we do have ions present to conduct electricity. Okay, but when I add the strong acid potassium hydroxide, remember strong alkaline potassium hydroxide, it can completely ionize to give me OH minus ions and K plus ions. It's a complete ionization. Okay, so this will be very steep because my OH minus off given is a lot. And okay, how do we compare to the at ST? Remember, this tartaric acid will only partially ionize. Okay, what's the formula? Okay, it will partially ionize to form hydrogen ions, which means that this rate, okay, the conductivity here is not as high as you would think because it's only partially ionized. Okay, which means that, okay, only these mobile ions are able to conduct. Okay, some of it remains as the tartaric acid molecule, which is unable to conduct electricity because this molecule itself is still considered is a simple molecular structure. So the amount of this, okay, because it's reversible, will be much less than this. Therefore, conductivity at ST is much lower than TU. So gradient is less steep. Okay, so you can say that, okay, excess KOH is present. KOH is a strong alkali, fully ionizes in water to give more mobile ions. Okay, and then there's lesser, or you can say there's lesser mobile ions for ST. Okay, you need to compare one to the other. Okay, which you look at here, the comparative term is lesser or more. Some of you just stated, okay, merely stated instead of comparing. Okay, next, question 4. Oxy acid is an acid that contains oxygen atom bonded to a hydrogen atom with at least one other element. Chlorine forms several types of oxy acids. Okay, table below shows some oxide acids of chlorine that are the same concentration. So you have perchlorate, you have hypochlorous, chlorate, and chlorous. Formula are given. Okay, and they tell you observation when the reaction in magnesium. Okay, perchlorate gives you very vigorous reaction. Hypochlorous few bubbles seen. Chloric acid vigorous, and chlorus reacts readily. So in terms of part A asks you in increasing order the strength of the oxy acids, which means that the most vigorous reaction, okay, will be the strongest acid. Okay, so perchloric acid will be the strongest. Then next, vigorous, followed by reacts readily and few bubbles. Okay, so answer is from least strong to the strongest, weakest to the strongest is is the HOCl, which is your hypochlorous, followed by your chlorous acid, okay, followed by your chloric acid, and lastly your perchloric acid is the strongest. Okay, of course, remember we do not compare acid strength by saying one is stronger than the other, but just that in this case they want you to rank in increasing order. So I have to use the term stronger or weaker to compare. Okay, next, part B. Hypochlorous is a weak acid or found naturally in the white blood cells of mammals. Do you think this is important? It's just context, you can ignore. Okay, when dissolved, the hypochlorite ions is formed. This is very important. They are giving you a clue to the answer. So please, you might want to underline this or box this up in your exam. Okay, it's found to have strong disinfective properties and has been identified as an ideal cleaning agent and sanitizer. Is that important? Not really. Okay, so okay, they ask you what is meant by weak acid. Remember, okay, if you want to explain what a weak acid is, you have to both talk about the fact that it's an acid, okay, and then it is partially ionized. So you'll say substance that is, okay, dissociate or ionize partially in water to produce hydrogen ions. A lot of you forgot about the hydrogen ions portion. You have to still explain that it is an acid because it is in bracketed. Okay, so you have to explain the acid portion as well, which is give off H plus ions. Okay, hence write the equation to show that it ionizes, how it ionizes in water. Okay, hypochlorous, remember few bubbles seen is weak acid. Oh, they already said there is a weak acid. Has to be a reversible sign. A lot of you are writing the wrong reversible sign. You are just putting two arrows opposite direction. This is wrong. Okay, it's two half arrows facing opposite directions. Okay, so since it is a weak acid, okay, it will form H plus definitely, but how many moles of H plus form we do not know yet. You have to compare to the hypochlorite ion ClO minus. Okay, if you inverted it and put OCl minus, also accepted. But since it's already given in the question, please utilize the information. Okay, to balance out ClO minus, you need one mole of H plus. Okay, part 3. Reaction of magnesium with perchloric acid is more vigorous. Okay, they already told you. However, both will produce the same volume of gas. Explain why is this so. First, okay, there's a few ways to approach this question. Okay, one is you tell me that both acids are monobasic. Monobasic meaning they give off the same amount, the basicity is the same, or they give off the same number of moles of hydrogen. Okay, so you are trying to compare hypochlorous with perchloric. Notice they both give off 1 mole of H plus ions for 1 mole of acid. Okay, so since they are monobasic, they will give you the same, when they are fully reacted, they will give you the same volume of products, the volume of gas or mass of salt. Because the reaction itself of the acid plus the metal, it is one direction. The strength of the acid only affects how the rate at which the H plus is given out, being produced or ionized. Eventually, with enough time, okay, even a weak acid can completely ionize. But you need a lot of time because it's a reversible reaction. It will keep reversing. Okay? But once you remember, the key here is once you form the salt. Okay, giving an example. Let's say once using the previous example. Okay, once I form the salt here, it's irreversible. Okay, so I keep forming the salt, eventually the same mass of salt will be formed because this reaction of the weak acid plus the metal is one direction. Okay, other ways to answer is you can say in terms of describing the basicity, one H plus ion formed when one molecule of acid ionizes, okay, or one mole of H plus ions formed when one mole of acid ionized, or lastly you tell me the magnesium or the acid is the limiting. So it doesn't matter, because as long as the concentration of either the metal or the acid is the same, the reaction will still proceed to completion eventually. So it's a timing issue. If you are talking about the rate of the effervescence form, definitely perchloric acid will give you far more vigorous effervescence because of the rate of formation. The rate at which the H plus ions are being produced from the acid is much faster than that of the weak acid. Okay, so please get this concept right. Regardless of whether you have a weak acid or a strong acid, when they react to form a salt, okay, it's always once the salt is formed, that's it. Okay, and as long as the acid can keep churning out the H plus ions, regardless of whether it's a weak acid or strong acid, eventually they will produce the same moles or mass or volume of the salt or the gas respectively. Okay, next question 5. Okay, solution of different acids of the same concentration have different properties. The concentration of hydrogen ions, pH and rate of reactions with metals and carbonates may be different even when the initial concentration is the same. So what is this trying to tell you? Okay, this question, they're trying to tell you that it doesn't matter about my concentration, it doesn't matter about my concentration. If I have different acid, they might give me different pH even with the same concentration. Okay, so example, hydrochloric acid at 0.01 mole per dm cube, it will give me pH 2, but sulfuric acid at 0.01 mole per dm cube, it will give me 1.7 pH. Why is that the case? Even though same concentration, notice that it's because of the hydrogen ions present. Concentration is different despite the initial concentration of the acid being the same. Next, if we look at ethanoic acid, 0.01 is much higher pH of 3.4, but we know that ethanoic acid is weak, whereas the other two are strong, which ties in with what we know about strength of acids. The stronger the acid, the lower the pH. Strong acids will have low pH and weak acids will have high pH, closer to 7. Okay, so if we compare, there's many things we can compare from this table. Okay, next they ask you for general equations of reactions of acids. Some sources such as textbooks, okay, represent general formula as HA, where HA is an anion. HA can be used to give general equations for reactions of acids. For example, reaction of acids with group 2 metal hydroxides may be written as 2HA plus MOH2 give you Ma2 plus 2H2O. And the reaction of any acids with any metal can be shown as this. Okay, where X is the value of the positive charge of the metal ion. Okay, which acids in table 1.1 fit the general formula HA and which do not? Explain your reasoning with reference to the ions present. A lot of you didn't reference the ions present. You only reference H plus and you forgot about the N ion. Okay, in order to satisfy HA, okay, H is a H plus, which means I need a minus. So I need a N ion with a -1 charge. So I cannot use sulfurate because sulfurate is a SO42 minus N ion. I can use ethanoic acid and hydrochloric acid, okay, which will give me Cl minus and COO, HCH3COO minus ions respectively. Okay, so only hydrochloric acid and ethanoic acid fit. They are both monobasic, okay, with hydrochloric acid containing H plus and Cl minus, and ethanoic acid containing H plus and CH3COO minus ions. Next, construct general equation for the reaction of an acid with group 1 carbonates. Okay, use HA as the general formula of the acid, as M as the symbol for the group 1 metal. Okay, for group 1 they are plus charge, so to pair with a carbonate I need Mg2CO3. Okay, and then I balance with an acid, so I start with HA plus M2CO3. Remember your salt form will be A, Okay, A minus paired with M plus. Okay, so it's a M plus. So it's a Ma. And then CO2, H2O. To balance, I need 2Ha and 2Ma. Okay, part 3. Okay, write an equation for the reaction of calcium with ethanoic acid. Show with reference with the value of X why equation 2 agrees with your equation, which means whatever is mentioned here must be satisfied. Okay, so Ca plus ethanoic acid will give you calcium ethanoate plus hydrogen gas, because it's a metal plus acid reaction to give you salt plus hydrogen gas. You must tell me X is 2 as the value of the positive charge of calcium 2 plus. Calcium ion is also 2. A lot of you did not satisfy this portion. Okay? So you're just missing that part. Okay? B part I. Student looks at the data in table 1.1 and suggests the following relationship. The student says pH is inversely proportional to 1 over initial concentration of acid. Many of you use the math method whereby you change it to pH equals to K over initial concentration. Sure, as long as you can prove it. Okay, but a lot of you only use one set of data, which is insufficient. They said use data to show in relationship. Incorrect. How can you prove to me that's incorrect when you only use one set of data? You use one pH with one concentration and you solve for a K or whatever. You cannot prove that. Similar to math, to show whether a K is, you have to show that the K is constant. Okay, so there's many ways to do it. Okay, anyway, no matter which way you do, you'll notice that it's not true, as acids of the same concentration do not have the same pH value. Okay, so you can do it a few ways. One, you use same acid but you use different concentration and you show that it doesn't correspond, okay, to the pH. It is not 1 over. Or you can compare across different acids with the same concentration and you compare their pH. Either way works. Okay, so for this case, what I did was I chose initial concentration of acid. I used all 3 acids and they have different pH despite having same concentration. I show that this relationship is incorrect. Okay, next, state and explain the factors that affect the pH of an acid using information from table 1.1. A lot of you did not use information in the table. You only told me concentration of H plus affects the pH, and the more higher the concentration of H plus, the lower the pH. That is what you learned, but you are not using the data. Okay, this is a database question, which means you need to use data from the table. Okay, and in fact, okay, concentration of H plus is not a factor of the acid. It's a property of the acid. Okay, some of you made it very vague. You say type of acid, but that is way too vague. Okay, so if you notice just now, what if we compare, okay, if you write out the formula of the acids, you will notice that, okay, they are all different basicity. Okay, hydrochloric and ethanoic are both monobasic, but sulfuric acid is dibasic. For every mole of sulfuric acid, you will get 2 moles of hydrogen ions. Okay, which is reflected here. Here. Okay, double that of hydrochloric acid. Okay, second factor would be the strength. We compared already. Okay, strong versus weak. And last but not least will be initial concentration of acid, which a lot of you managed to get, and is the only factor you managed to quote. Okay, notice it's a 3-mark question. Main expectation will be at least you have to put 2 factors. Okay, so most of you got the last one. Concentration of acid will affect the pH, as the higher the initial concentration, the lower the pH. This applies to all acids. Okay, so how do we explain basicity? The higher the basicity, the lower the pH. So you can use concentration, you can compare hydrochloric acid and sulfuric acid. For both same initial concentration of 0.01 mole per dm cube, okay, hydrochloric acid will give off 1 mole less H plus ions than sulfuric acid. Therefore, okay, monobasic HCl will have pH of 2 compared to dibasic H2SO4 pH of 1.7. Because for every mole of sulfuric acid, you produce more H plus ions. Therefore, pH will be lower, even though the initial concentration of both acids are the same. Okay, last but not least, the strength of the acid. How does it affect pH? The higher the strength, the lower the pH. Which means strong acid, low pH, weak acid, higher pH. Okay, so you can compare hydrochloric acid with ethanoic acid because they are both monobasic. It will be difficult to compare a dibasic strong acid with a monobasic weak acid. So you must choose your comparison, what you compare very carefully. Okay, in this case we use 0.01 mole per dm cube hydrochloric acid and ethanoic acid. You are comparing weak and strong monobasic acids. Okay, the strong HCl will produce a pH of 2 compared to weak ethanoic acid with a pH of 3.4. Okay, so those are the three factors. Okay, some of you said initial concentration of acid and concentration of H+, but you notice that concentration of H+ is dependent on the concentration of the acid. So it's like the same thing. You are saying the same thing but saying it as two different factors, but it's actually part of it. Okay, a lot of you failed to talk about the acid themselves. Okay, last but not least, complete table 1.2. Use the data in table 1.1 to help you. Okay, I think there was a typo in your worksheet. They said use data in 1.1, which is why a lot of you, I think you didn't refer back to this original table to obtain the pH. Okay, so for hydrochloric acid, concentration of acid is 0.04. Concentration of H+ ions will be the same because HCl will fully ionize to give H+ and Cl-. So it's a 1:1 ratio. Okay, so you read 0.04 H+ ion concentration for HCl. Okay, 0.04. Sorry, 0.04. Here is 1.4. Okay, you don't have to check for the same acid because remember we always said that pH is a measure of the concentration of H+ ion. So it doesn't matter what acid. Okay, ignore this portion, but this part will hold true. Okay, so remember earlier on we had that relationship question. This one is wrong because it's not initial concentration of acid but H+. Okay? And it's also not an inverse relationship lah. It's a logarithmic relationship. Okay? So this part will correct. This part always satisfy. Okay? Next, for sulfuric acid, remember it's H2SO4. Okay, so it's a dibasic acid. It will give you 2H+ plus Cl-. Oh, sorry, SO42-. Okay, so since it's 2H+, you must double the concentration of hydrogen ion, so you get 0.10. Okay, and then you read from the table 0.10 here, pH is 1. Okay, pH is 1. Okay, take note for pH, there's no need to 3SF it because pH will only go to 1 dP. Okay, mostly 1 dP. Okay, but for concentration, please remember to stick to 3SF because it's still a number. Okay, it's a calculated number. Okay. Okay, so last but not least, please revise this worksheet a lot because a lot of you didn't do well for it.